Hello everyone, welcome to VLSICareerCraft. This is Monica, and today in this video we'll discuss an important interview concept, that is how do we fix the setup violation. So far we have seen why do this setup and hold violations exist in a design, and we have derived the equations for this violation checking. So now let's see how do we fix this violation when they actually exist in the design. So let's get started. Now let's start with a brief overview of setup timing check. So when we have a register based design like this, that is when we have a launch flop which is launching data and capture flop which is capturing data, and in between if there is any combinational logic, then how do we check the setup timing here? So let's understand from this waveform. For the detailed step-to-step derivation, you can refer to my previous video so that you can get a better understanding. So here, this is a launch clock path, and this second one is the capture clock path. So when we consider all kinds of delay, that is launch delay which exists in the launch clock path, and the capture latency which exists in the capture clock path, and the additional delays, those are T clock to queue and T combinational delay. So here what is expected, like when all delays are considered, the data is launched at this point and the data is expected to be ready at this point, that is certain time before the capture clockage arrives, that is nothing but the setup time. So when the data is ready at this point or before this point, we are fine, we are good, and the data is captured correctly. But if in any case, if the data is not ready at this point, there is a setup violation. That is, if T clock to queue, the maximum delays are considered for clock to queue and combinational to consider the worst case. And again, the worst case is also explained in the previous video. And the setup time is also considered. So if this less than or equal to condition does not obey, then there exists a setup violation. Now, how do we fix this violation? Let's see few ways how we can fix it. So the first and most commonly used method for fixing setup violation is increasing the clock period. Increasing in clock period is nothing but decreasing the clock frequency. So let's understand through some waveforms. Let's say in this case, the data is expected to arrive at this point, but the data is arriving at this point somewhat late than what we are expecting. So this condition and the setup equation condition is not satisfied. It's not greater than or equal to. So there exists a setup violation here. So how do this get resolved when we increase the clock period? Let's say in this waveforms, we have increased the clock period. So what happens here? The data is expected to arrive at this point, and the data is arriving at this point, which is somewhat before the point where we are expecting. So this allows a certain time frame for data to arrive. That is, at any point here, the data can arrive for getting properly captured by the capture flop, and this condition gets satisfied, and which in turn resolves the setup violation. So but what is the problem with this method of fixing setup violation? We are decreasing the clock frequency, that is we are slowing down the system, we are decreasing the speed at which the system is operating. So this degrades the performance of the product. Coming to the second method of fixing setup violation, that is by increasing the clock skew. How do we increase the clock skew? If we look at this equation of the skew, if we increase the capture latency, then the skew will be automatically increased. We already know what is capture and launch latency. Once again, the delay which exists in the capture clock path is referred to as capture latency, and the delay in the launch clock path is referred to as launch latency. So, how does this solve the setup violation? Let's understand from this these waveforms. Let's say there is a setup violation in this case. That is, data is expected at this point, but it is arriving at this point somewhat delayed. So there is a setup violation. So let's add some additional buffers in the capture clock path to increase the capture latency. So the waveform will be like this after increasing the capture latency. So if you see, the capture clock is starting somewhat later than this case. So the setup violation, the time frame, here we don't have any time frame, and there is a violation here. But in this case, if we see, the data is expected to arrive at this point, but it is arriving at this point. So there is a lot of time frame in for the data to arrive. So it will be captured correctly, and the setup violation is resolved here. So we can understand this by looking at this equation as well. If you increase the right hand side of the equation, any term right hand side of this equation will satisfy this condition, because the right hand side should be greater than or equal to the left hand side. So here the t clock we have increased in the previous method. Now in this method we are targeting this q, and if we increase this q, then initially for the case which this condition is not satisfied, will be satisfied automatically after increasing this. So yeah, this is the second method of fixing setup violation. Coming to the third method of fixing setup violation, that is modification of architecture. So by modifying the architecture, what are we doing? We are reducing the delay of the combinational logic. So in the previous two methods, what we have seen, we have increased the skew, we have increased the clock period. So right hand side, we are like we already have two methods of fixing the setup violation. But if you observe the left hand side, which we are supposed to decrease in order to satisfy this condition less than or equal to, so we target combinational delay. How do we modify the architecture? For example, let's say the combinational logic between this launch flop and capture flop is a ripple carry adder. We all know that ripple carry adder takes the smaller area, but the delay of the this architecture of the adder is somewhat higher. So when we move to the more advanced architecture to reduce the delay, that is carry look ahead adder. So if we replace the ripple carry adder by carry look ahead adder, the delay is reduced, that is the combinational max is also reduced, which in turn helps in satisfying this equation and eliminating the setup violation. But what is the problem here? So yeah, we all know this ripple carry adder's delay is greater than the carry look ahead adder delay. But the area and power of carry look ahead adder is higher than the previous architecture, that is ripple carry adder. So we have to compromise on the area and power just for the sake of fixing this setup violation by reducing the delay. So there is a trade-off here. Now let's think like an RTL design engineer. Let's try to make the modifications to the RTL code to reduce the combinational delay. We all know that RTL code will be synthesized into logic gates which account for the combinational delay while doing timing analysis. Let's say in the first case I'm using if-else statement, and in the second case I'm using case statement. So what is the difference between these two, and how does this decrease the combinational delay? Let's see. If else statement is a sequential evaluation. Let's say if the first condition is not satisfied, then only it goes to the second condition. So it executes one after the other, sequential execution. Whereas in the case statement, all the statements are executed parallelly, and it sees which condition is getting satisfied. So this is a parallel execution. So obviously parallel execution has the lesser delay. And also when if else statement is synthesized onto a hardware, it will be synthesized into priority encoder. That is, based on the priority, it selects the output. Whereas in the case statement, it will be synthesized into a multiplexer. So multiplexer selects one of the input based on the select line. So it is a simple logic and has the lesser delay. So making changes to the RTL code is reducing the combinational delay on the hardware. This is one of the method which is used to fix the setup violation. Now let's again think like an RTL design engineer. So here what we are doing, we are trying to change the architecture which is used traditionally like launch flop, capture flop and combinational logic. Now the combination logic is having 4 picosecond delay, let's say, which is hard to satisfy this equation, which is too high to satisfy this equation. Now what I'll do, I'll split this combinational logic into two parts and add a pipeline register in between. So this is executed and the data is launched here, and then this is executed. Both the functionings are same, but the extra register is added here in order to reduce the effective combinational delay. So when I split this into two, let's say each combinational logic is having 2 picosecond delay now, which is enough to satisfy this equation. So this is nothing but pipelining the design. So this pipelining design will helps us to reduce the combinational logic and fix the setup violation. So one more method of fixing setup violation is retiming the design. What is meant by retiming? Let's say I have this pipeline design and I have two stages. This is one stage and this is the second stage. So what are the combinational delays here? So I have 50 plus 20, that is 70 picoseconds of combinational delay here and 10 picosecond. So we consider the worst case for setup violation. So I see 70 picoseconds is very high to satisfy this equation. So I'm having a setup violation here. So what will I do? I'll push this recombinational logic 2 block into the next pipeline stage and keep this combinational logic 1 here in the first stage. So what will it do? It will make the combinational delay max as 50 picosecond now, which is 70 initially. So I'm reducing it and this is helping me to satisfy this setup violation check equation. So this is the simple example of how we retime the design. But on the real designs which are in the industry, it needs tools to retime it. And this is also one of the method which is used in fixing the setup violation. Now, one more method of fixing setup violation is upsizing the cells. Let's say I have two small buffers which are sitting in between the launch flop and capture flop. So these two buffers are contributing the delay of 5 picosecond, and it is higher for me to satisfy the setup time check equation. So what I'll do, I'll increase the sizes of these buffers so that the delay of the buffers is reduced to almost half, that is 2.5 picosecond. So why does delay decrease when the size is increased? When the size of the buffer is increased, it is having higher capacitance and it is easy to charge and discharge while transition from 0 to 1 or 1 to 0. That is, it is having lesser delay and good drive strength. So that is why this increasing the size of the logic gates help in reducing the combinational delay. Now let's see one more interesting method to fix setup violation, that is breaking longer nets. Now let's say this buffer is trying to drive a very long net and it is connected to other buffer, and this complete logic is between the two flops, launch flop and capture flop. So why is this buffer taking so long to make a transition from 0 to 1? Because This long net is having higher resistance and higher capacitance, and the delay is nothing but R into C. When this buffer is trying to drive such a long net, it is very difficult for it to make a transition from one state to other. So it is taking 100 picosecond, and this net is offering 10 picosecond of delay, and this buffer which is at the other end is also taking 100 picosecond. So what is the effective combinational delay? It is 210 picosecond. Now, in the second case, I am trying to break the net into two parts. So this buffer now is driving the shorter net compared to the first case. So it makes a transition which is better than the first case. Let's say now it is taking 60 picosecond and these two nets are taking 5 picosecond, and the buffer which is sitting in between these two is taking 65 picoseconds of delay. So what is the effective combinational delay here? 195 picosecond, which is somewhat lesser than the first case. So let's reduce it further by breaking the net into three parts now. Now we need to use the inverters connected back to back so that we don't want to change the logic here. So this buffer is trying to drive even more shorter net than previous two cases. So the transition is much better, and the delay which it is offering is 30 picosecond now. And this three nets combinedly offer 10 picosecond, which is unchanged, and these inverters are offering 35 and 30, which are driving shorter nets. So the effective delay will be 135 picosecond, which is much lower. So in this case, we are trying to reduce the combinational delay, which in turn helps us to satisfy the setup check equation and helps us to fix the setup violation. Now, in the previous case, we have seen reducing the wire length to reduce the overall delay. Now, as the delay depends on both resistance and capacitance, we can also reduce capacitance of the wire to reduce the overall delay. How do we reduce it? If in case I have a critical signals which are offering the higher delay and showing up set of violations. When we route these type of critical signals with higher metal layers, if you see in this diagram, the higher metal layers are sitting far away from the silicon substrate. This is the silicon substrate, and the higher metal layers are all these. So when I increase the distance from the silicon substrate, I'm obviously reducing the capacitance. So when I route critical signals with higher metal layers, it will obviously contribute in some reduction of the delay. So one more case where the distance helps in reducing the capacitance is when I have multiple wires which are getting routed, and when I see few wires which are sitting closer to each other. Let's say this is the default spacing, and they are offering certain coupling capacitances between the parallel wires. So these capacitances also contribute to this delay. So how do I reduce it? I try to move these wires far, and I'll try to reduce this delay. So in this way, I can reduce the overall delay and help to satisfy the setup timing check equation. Now, one more method of reducing the setup violations is optimizing the floor plan. So let's say I have a chip which are having 4 blocks, and they need to be connected to the IO ports. This IO port is connected to block 1 and this one is connected to block 2. If you see, there is a large net which is going from block 1 to all the way to IO port 1. So this is offering a large resistance and capacitance, and which is contributing to the delay. Now what do I do? Like, I make the changes to the floor plan and bring this block 1 and block 2 closer to the IO ports, and push this block 3 and 4 back. So it'll make the net shorter and which offers a lesser delay, and it helps in fixing the setup violation. So I hope you all understood the 10 ways of fixing setup violation, and in next video let's come up with the more interesting interview concept. And yeah, thanks for watching. Happy learning.